I want to just now start this final session of the symposium this afternoon, and it's a great pleasure to introduce a second Crafoord laureate from 2002, Dan McKenzie from the Bullard Labs in Cambridge. And Dan could probably talk pretty much about anything from Icelandic basalt geochemistry to tectonics of Venus. But today we've sort of tied him down to the symposium theme, and he's going to tell us about the deep structure of the continents. Dan.
Thank you. I'm told I have to be very careful because of my foot, that the crown princess here had the same problem, but she got it from skiing. And when she was giving a talk here, she fell off the platform. And I should explain that because everybody asked me, I was chasing ducks from a pond and I tore my Achilles tendon. I'm very pleased to be here to talk at Peter's prize giving. I first met Peter when he was a graduate student and I was a young postdoc at Lamont, and he taught me how to read fault plane solutions, a thing of which I've always been very grateful and have then made tremendous use of it in the western part of the Alpine Himalayan belt. Now, I'm not going to talk about that at all. We have actually worked together on two papers, one of which was really very uncontroversial, which was sorting out the triple junction at the southern end of the Red Sea, and that, as far as I know, everybody now more or less agrees with what we said then. The second one is a completely different enterprise. It's a paper that is known as Hausmann et al., right? And this has something like 500 citations. Greg Hausmann was a graduate student of mine, right? And Peter is part of the et al., and so am I. And I'm very glad that I am et al., right? Because I now do not agree with what we did at that time. And I'm going to explain why this afternoon. And I would say to various people that various things about all that. One is that if you're et al., no one ever knows that you're et al., right? They never read that bit. The other one is that what I think we did then was intelligent and worthwhile, but was wrong, right? Now, I never mind being wrong. I mind being stupid, right? And I don't think it was stupid. And I put this in the abstract I sent, and this got removed as being too rude to Peter. But Peter had encouraged me to say this, so I didn't feel at all badly about saying it rather publicly. So what I want really to talk about is why have I changed my mind? The reason why I've changed my mind is actually nothing to do with working on Tibet or on any of these questions. And it comes really from some work I've been doing with Keith Priestley on the deep structure of the continents. And what we wanted to do was to try and understand the geometry, the structure, the architecture of continental crust. And this is a typical thing of North America. This is from Holmes's book, which is what I was brought up on as an undergraduate, showing the Canadian Shield and then younger mountain belts stuck round the edge. Well, in the oceans, you don't get anything like this. This is all older. This part here is older by a long way than the oldest part of the oceans. Now, the oceans have spreading ridges and subduction zones and are really very easy in some sense to understand. This is not. We're looking at what has happened a very long time ago, right? And what has actually controlled the geometry of these mountain belts here in North America, and I'll show you some also from Central Asia. Various people who had most of this symposium have been concerned with that. And what Keith and I were interested in was in using surface waves to look at surface wave tomography in the oceans and continents. And Keith, now, the model I'll show you, has made use of 5 million seismograms, the total amount of data being about 20 terabytes. So processing this, even now with modern machines, is really quite a challenge, because that's really an awful lot of data. You really push all the storage and everything. And what Keith has been doing is using, particularly, here are the fundamental mode Rayleigh waves, but particularly what are called higher modes. And higher modes, the great thing about higher modes, and I'll show you their displacement as a function of depth in a minute, but the great thing about them is that they only exist because the velocity in the Earth increases with depth. If it doesn't, you don't get higher modes. And the great advantage of using higher modes, it's the same picture, the higher modes which come between the S waves and the fundamental waves, is that their displacements, here's the fundamental mode, right, whose displacement dies away exponentially with depth. The higher modes wiggle. And the great thing about the wiggling is that this allows you then to use different combinations of higher modes to look at the velocity at different depths. So a lot of the resolution, and I'm only going to really talk about the top, I mean, this is top 300 kilometers down to about here. The resolution comes from the fact that these wiggle in different ways. And we use the fundamental mode and up to the fourth higher mode, right, and use their travel times to essentially work out the velocity structure of the upper mantle. And this is the fundamental method which everybody really now uses. And the great advantage of this is that these things travel everywhere. If I were to show you a picture of Asia with the tracks on it, with the paths on it, right, Asia would be simply totally red, right? Because with 5 million paths, right, you really don't see any details. Right? And that's a tremendous advantage. Now, this picture was one which we made, here is America, and this we made of the velocity, the shear wave velocity from this tomography, at a depth of 50 kilometers. And you can see here's the East Pacific rise. When we made this picture, I thought, oh dear, we got an artifact, because this thing here looked to me like the spreading ridge here, and I had hoped that this particular method of inversion that we used was free of artifacts. Well, Peter, when he saw this, said to me, didn't you know about the evolution of the Pacific? And I said, no, I didn't. I've worked on the Indian Ocean, but not the Pacific. He's worked on the Pacific. There was a ridge jump. Here is the original spreading position of the ridge, and during anomaly 5 time, about 10, 15 million years ago, it jumped westwards. And so what we're seeing here, right, we've resolved a piece of essentially oceanic tectonics, which I didn't know about. This isn't an artifact, this is real. And this shows that the resolution of all these 5 million seismograms is actually fairly close to what Keith hoped, which was something like a horizontal resolution of 250 kilometers. The vertical resolution is about 30 kilometers. So that was really upsetting to me at the beginning until I realized what we were looking at, and then very satisfying. Now, the next thing which I need to explain is that the shear wave velocity, right, and it is dependent not on the composition, but on the temperature. This shows what happens to the shear wave velocity when you take an ordinary piece of fertile upper mantle and remove melt from it. What happens to the composition is that you remove garnet and clinopyroxene preferentially, right? The rest, what remainder after all these things is olivine, and the orthopyroxene remains more or less constant. So you end up here, right, after taking out about 25% of melt, you end up with a Hartsbergite. And that's important. Now, the change that you make in the shear wave velocity goes from 4.85 to about 4.87. 7. So it's really small. And the shear wave velocity changes I'm going to show you in a minute are between 4.8 and 3.8. So they're very large compared with this. So that means that from the point of view of composition, we can ignore changes in composition. We're only, with the shear wave velocities, looking at the temperature. Now, this is both an advantage and a disadvantage. The advantage is that you know what you're doing. The disadvantage is that you don't get any information about the density. When you remove the garnet from here particularly, garnet goes, and so does iron, the density changes by something which doesn't really look very important, right here, but that corresponds to the change in density. If that was produced by temperature, you'd need about 500 degrees centigrade change in temperature to produce that change in density. So the depletion has an enormous effect compared on the density. And in particular, it can do various things to the mantle. So that's the background, that shear wave velocities looks at temperature, doesn't look at composition. We need some other method of looking at composition. I'll come back to that in a minute. So this is what we then did. There's been a lot of efforts to turn shear wave velocity, to know what the function is that turns shear wave velocity into temperature. What we decided to do, and I'm not going to go through it in detail because it's published, right, is essentially to use what we knew about the Earth to parameterize the relationship between the shear wave velocity and temperature simply by using geophysical observations. We used the velocity, here's the shear wave velocity stacked as a function of age in the Pacific. And you can see, if you didn't believe in plate tectonics before this, you can see exactly what we have always believed here, which is that the temperature below the spreading ridges, right, is essentially the same below a depth of about 150 kilometers everywhere, and that the plate is essentially a boundary layer which is cooling, and as it cools, the seismic velocity increases. Well, we also know from plate models here what the temperature is as a function of depth, so we can combine those two together to get the shear wave velocity as a function of the temperature. And this behavior is typical, right, of what is also seen in the lab. The problem with the lab experiments is that they're all done with grain sizes of microns. And it's clearly what this part here, which is part that really matters, that behavior depends on the grain size. And to go from the laboratory to the mantle, right, where we don't know the grain size anyway, but we think it's about 1 millimeter, is an extrapolation over 3 orders of magnitude with no decent theory. So I think it's preferable to use the geophysical observations and geological observations to actually get that relationship. So this is part of how we do it. This gives us the relationship at shallow depths, right, and at fairly low temperatures. We can get various other things, right, and that is it. And we also use the temperature and pressure estimates from nodules and kimberlites, right, and use the fact that we have a global seismic tomography, so we can use the velocity structure at the site of the kimberlites, right, and look then at what the velocity is at the depths from which the nodules are coming. One of the other things that's important to do in the oceans is to remove regions which have funny crustal structure. These regions here, from some work which one of my graduate students said, he outlined the regions here by hand, right, to remove regions which he thought were anomalous. And removing these from the shear wave velocity estimates has had a very big effect. Here is without doing that. You can see that the errors in the fit, well, the errors, and this variation is variation in the stack profiles, is large compared with what it is now. It went down a huge amount when we removed the Alistair Crosby's areas which he thought were anomalous. And here then are the fits, right? The dashed lines here, right, and the solid lines here are the fits to the data, right, just for the oceans. These are this is nodule data. And in general, we can do really quite a good job now at reproducing all the data, all the temperature estimates that we have simply from the measured velocities. So that's what we do with that. And then we turn that into a lithospheric thickness by fitting a standard geotherm to the matter. Right. Well, this is what we did in 2006 for Africa. And this is the... No, that's from... this is from... Sorry, this is from Ritzimer's surface wave tomography. Exactly the same approach, using his data everywhere. And this is what we get. And you can see, first of all, they agree rather well. Secondly, I think our resolution is a little bit better. You can see these are the regions where the cratons are exposed. And you can see that, for instance, here in East Africa, there's thin lithosphere just along the axis of the East African rift. And the method only works when the lithosphere is greater than about 110 kilometers. That's for rather technical reasons, which I don't need to go into here. It's to do with the fact that we can only use surface waves, right, whose period is longer than about 50 seconds, because otherwise they don't travel along great circles. So we think we can now produce maps of the lithospheric thickness for the world's continents using this approach. And these red dots, these are diamond-bearing kimberlites. And you can see that they fall all within the diamond stability field, right, requires a lithospheric thickness of greater than about 160 kilometers. So these things should all fall within the region. Right, the thick black line is the 160 kilometers in the white strip, and you can see all of these fall within that region. We can do a little bit better. We can look in a bit more detail. Here's South Africa, where we have a lot of information from the kimberlites. Here are the contours of the lithospheric thickness, and these are the lithospheric thickness from fitting the PT estimates from the nodules. The root mean square difference between these two is about 25 kilometers. And I don't believe any of the estimates from any of these methods are better than 25 kilometers. So what do these things look like? Well, Africa, right, Africa, this is the gravity and this is the topography. From the filtered gravity, it's from GRACE, which is satellite data. You can see here that all these things here, that's Tibesti, Haga, Darfur, all these things are plumes, right? These are the surface expression of plumes, which are all the places here in the topography where the topography is elevated. And actually, the settlement of Africa by the white settlers is completely controlled by where the plumes are, right? They must have known, right? Because they stick high enough up in the air for the sort of agriculture that the white settlers were used to be carried out. And that's throughout the whole of southern Africa. Even the plume elevations here, right? The thing is still too hot. You can't do anything in the middle of the Sahara. Now, if I compare that here with the lithospheric map, you can see that in the regions where the plumes are, particularly in Angola and further south, these are regions where the lithosphere is thin. Now, the question which I don't know the answer to is whether the location of the plumes is controlled by the lithospheric thickness or vice versa. Right? We all think of the lithosphere, the lower part of the lithosphere, as being attached to the crust on top, but I am beginning to suspect that convective circulation may be able to move the lower part of the lithosphere around. I don't know. That's one thing which is not sorted out by all this, right? And it's what I'm suspicious of is, of course, that the agreement with the lithospheric thickness with the kimberlite nodules, the kimberlites are mostly Cretaceous or Jurassic, and the lithospheric thickness doesn't seem to have changed since then. Right? So it looks to me as if it's the opposite way round to what one might think, right? That actually the convective pattern locks onto the lithosphere and is carried around with it, rather than moving it around. Now, here's North America. Here are the diamond-bearing kimberlites all over North America. They go right down to Arkansas. Right? There's a kimberlite pipe in Arkansas, which is a tourist attraction. The people who own it buy poor quality diamonds and put it into the kimberlite and then charge the tourists to come and sift through all this dirt and find their poor diamonds. They make a lot of money out of this. But in general, you can see this is the surface outcrop of the shield, but you can see something which is quite general, which is that the thick lithosphere extends way beyond the boundaries of the surface outcrop, and indeed there are places here and down here where the thick where there's thin skin tectonics, which has brought things, brought the thrust of carried things 100 or 200 kilometers across the thick lithosphere. So that's all fine. And South America, this is something which I didn't know, which I discovered last week, is that this area here, all the way up on the eastern side of the Andes, so the oily men tell me, right, was back arc spreading, which is now being shortened and overthrust here by the Andes, which is now bending this down and producing a large gravity anomaly all the way down here. But what about Asia? Part of Asia is what I expected. Here is the Russian platform, thick lithosphere. There's a step. This boundary here, 60 degrees east, is where the Urals are. And the West Siberian Basin, which is this area here, which has subsided at a fairly steady rate from the Jurassic, since the Jurassic, for reasons which are completely unclear, right, that is a little bit thinner than over here, but still quite thick. But the real surprise, and this is skip the Arctic, but the real surprise to me was Central Asia. This is the area, This is the area, right, of Tibet. Here are the earthquakes, which Peter and I and Greg Hausman said had thin lithosphere and that it had detached. Well, it doesn't. It actually has the thickest lithosphere on the planet. And now we've got better resolution. You can see it's not just Tibet, but you can see here the Tian Shan also have thick lithosphere, and so do the Zagros. And these are the regions, this is the topography. You can see here the Zagros high, Tian Shan high, and Tibet. So anyone looking at this map says the obvious thing, which is that maybe what's going on is that actually the thick lithosphere is produced by shortening. Right? And so is the thick crust, and that's why there's elevation. Well, you can test that out simply by doing the sums and say that you are going to predict the lithospheric thickness simply from the elevation. This is what Peter showed earlier on, of the thing falling off. Well, that clearly, I think, now does not happen. So what about making it by shortening? You shorten the thing here, you start off like that. Lithospheric thickness, and the one I'll show you is for 110 kilometers. Shorten it, use the elevation to actually get the lithospheric thickness. And this is what you get. Here is it calculated from the elevation, and here is it what we observe. And I particularly point out these features, right, the Zagros, right, and the Tian Shan here. Now, in some sense, with Tibet, I think this is a bit of a fudge, because I personally believe, and I don't think Peter does, that the southern half of Tibet is essentially sitting on top of Indian lithosphere, which has been shoved underneath. But with the shortening here, that's very clear. Now, the next question comes as to why, if this is what's gone on, right, why has it not fallen off in the way that Greg Hausman and I and Peter thought, and Peter went through this morning? Well, you can do a little bit more than this. you can actually look at what the composition of the melts are that Peter was talking about. And you can model that. And what we know that with kimberlites, right, and these are the ones that, for instance, in South Africa, is that what happened there was that these things are made by, first of all, melting a great deal of the crust, sorry, the mantle, and you melt it actually in a particular depth range. You mustn't melt it too deep and you mustn't melt it too shallow. And it particularly is not extracted, the melt cannot be extracted at the depth that this material is now. So you melt and extract, and then you have to shorten it to take this material down. And the geochemical arguments for the depth of extraction are really because of the fact that certain elements, like yttrium, ytterbium and lutetium and vanadium, right, are retained, some of them by garnet and some of them by spinel. So you can actually constrain the depth at which the initial extraction comes quite accurately. Then you shorten it. Then you've got to enrich, right, because the depletion here produces a Harzbergite. We need a Harzbergite which has been slightly enriched by about 2% in order to produce the source of the kimberlites. And then we can melt and make the kimberlites or whatever we want to in terms of the composition. And I'm not going to get into the arguments about how you should name these alkaline rocks, right? I think of petrology in terms of komatiites, basalts, alkali basalts, and alkaline rocks, right? And I don't think one need, if you're a geophysicist certainly, to make very careful distinctions between lamprophiles and lamproites and alnoites and all the rest of them. Anyway, this is the composition of some melts, which alkaline rocks, which are erupted in northern Tibet, right, which have extreme enrichment in the light rare earth elements. And you can't get this enrichment by melting even very, very little bits of the normal mantle. You have to have a really depleted source to get the bulk partition coefficients down sufficiently to actually be able to do this. And then you need, after that depletion, making essentially what is a Harzbergite, you put in a little bit of melt, and then if you melt, because the bulk partition coefficient is so small, you can make very small amounts of these extremely enriched melts. And that's one of the features both of kimberlites and of the melts in northern Tibet. They're quite small volume. The bit which tells you what has gone on is what happens down here. Right? To get this thing to flatten in this way, that's what tells you the depth of the original depletion. Now, once you know what the source is, then you can calculate its density. Right? And these are the densities of the sources relative to the convecting upper mantle. And this is purely compositional. I'm ignoring the temperature. So these regions here in Tibet and also in the Zagros, these are about 60 kilograms per cubic meter lighter, right, than the mantle at the same temperature. How much do you have to cool the mantle, right, to get, how cold do you have to make these things before they'll sink? About 500 degrees. And if you cool this by 500 degrees, the viscosity is so large, you're not going to budge it. So the reason, I believe, why this region has this thick lithosphere is simply that it's Harzbergite. And the final part of this story is that Tibet now has a thickness of something like 70 or 80 kilometers. And if you look at the thermal evolution of this, which I'm not going to go through, the hottest part of the whole of the lithosphere is at the center of the crust. So if you erode this, right, what you end up with, what you would then end up with, is 30, 40 kilometers of crust with very high temperature, 1,000, 1,100 degrees centigrade, metamorphic minerals at the surface, despite the fact that you're sitting on top of lithosphere whose thickness is perhaps 260 kilometers. So if I come to the conclusions, right, I don't think that what Peter and I and Greg did was stupid. but I do think it's wrong. I think it's a good illustration of how, if you work on the edge, which certainly Peter and I have done throughout our careers, sometimes you get things right, and sometimes you get things wrong. If you get things wrong, provided you keep your mouth shut, nobody remembers. I have various papers which I wish I'd never written, right? But I never refer to, and nor does anyone else. They've just been forgotten. And people have, it's the way science works. People forget things that are wrong, right? Provided the authors themselves don't go on saying that I got it right. And I'm not prepared. I don't think I did get it right then, right? And I'm not prepared to stand up and say I did. I'm apologetic about having got it wrong, but it was, as I say, not, in my view, stupid, even though it was wrong. Thank you.